Hello and welcome. In today's video, we are looking into Hadoop Distributed File System and understanding of core concepts. And we will also see architecture, storage, replication, high availability of NameNode, and HDFS real world use cases. Before moving into HDFS, we have the volumes of data being generated in our user applications. The storage capacity of machine may often not enough to store all of it. However, this can be resolved if you store the data across a network of machines, and these networks of file systems are called as distributed file systems. So this is where Hadoop comes into play and provides a reliable file system commonly known as HDFS. It is unique design that provides storage for extremely large files. So now let's begin HDFS, understanding what is HDFS. As we all know, HDFS is Java based distributed file system designed to store very large data sets with reliability, and they can be accessed much faster. So it provides access to the data across Hadoop clusters. And what is a cluster? A cluster is a group of computers that work together using network. So like other Hadoop related technologies, HDFS is a key tool that manages and supports analysis of very large volumes like petabytes and even zettabytes of data. So why we are using HDFS? Before 2011, storing and retrieving huge amounts of data had the following three major challenges, which are number one, cost, speed, and reliability. So traditional file systems approximately cost $10,000 to $14,000 per terabyte. So you need to remember, so it costs a lot of high value. Searching and analyzing is very time consuming and very expensive as well. So also, if search components were saved on different servers, fetching data was very difficult. So let's see how HDFS overcome all these three challenges. So number one, cost. HDFS is open source, as we all know. So it can be used without any licensing or support costs. So it is designed to run on a regular computer also. So the first challenge is resolved because of it is open source. And then speed. Large Hadoop clusters can read or write more than terabyte of data per second. So it reads terabyte of data per second, and a cluster comprises multiple systems logically interconnected in the same network. So the clusters are logically interconnected, and the speed of writing and reading is very high compared to traditional systems. HDFS can easily deliver more than 2 gigabytes of data per second to each MapReduce, which is a data processing framework of Hadoop. So we need to remember it can read and write terabyte of data per second, and then 2 gigabytes of data it can deliver to MapReduce framework. So the second challenge is now resolved. Let's see reliability. HDFS copies the data multiple times and distributes the copies into different nodes, which is called as data blocks. And a node is a commodity server which is interconnected through network device. HDFS then places at least one copy per node and the other copies in individual nodes. In case of any data is deleted from any computer node, then it can be found and recovered from other node of the cluster. So the data is never lost. And a regular file system like Linux file system is different from HDFS with respect to the size of the data. And another one, each block of data is small, usually about 51 bytes. However, in HDFS, the block size is 128 megabytes by default. It can be varied based on default settings. You can increase it to 128 MB to 256 MB also. So these are two basic values that we set in our configuration. A regular file system provides access to large data but may suffer disk I/O problems mainly due to multiple seek operations. On the other hand, HDFS can read large quantities of data sequentially after a single seek operation. So this is where HDFS is unique in providing data with its high capability comparing to traditional file storage systems. And so here is the basic architecture of HDFS, and the architecture is following master slave method, wherein master is NameNode. NameNode is again a component of HDFS, and we have another one, secondary NameNode, which is not shown here. It is another component of HDFS, which is standby of primary NameNode. And then the third one, DataNode, as we see here, each DataNode is a slave here, and it has been managed by resource manager of NameNode. And if you see within the slave, we have node manager and then MapReduce. Let's move and see the full architecture like here. So the NameNode is the active master and the secondary NameNode is the standby, which is the exact copy of primary NameNode. So as we see, we have job tracker which tracks all the read-write requests from the client, and it maintains heartbeats, balancing, replication of data that is stored as blocks in data nodes. So whenever there is a client request, so NameNode provides the location, metadata for that particular file, and the client can access the file directly from data nodes. So this is basic architecture of HDFS, and then let's move to the details of each and every component. Before going to NameNode, let's recollect the main characteristics of our HDFS. So number one is HDFS is high fault tolerance, and it is having high throughput, and it is economical. As we have seen, it is a open source, and it is being designed to support large datasets in batch style. It is specifically for batch jobs. However, the emphasis is on high throughput of data access rather than low latency. And then it can be built on commodity hardware and heterogeneous platforms as well, which is low priced and easily available. And the last one, HDFS is designed to store and scan millions of rows of data to count or add some subsets of the data. The time required in this process is dependent on the complexities involved. So, these are main characteristics of HDFS. And then, if we recollect, we have even seen HDFS has standby node, and let's see in detail how HDFS works. So let's take an example of a patron gifted a collection of popular books to a college library. So the library has to be arranged in such a way the books can be accessed by the students in a easier manner. So the job is to the librarian who acts as a resource manager in our architecture. So he decides to arrange the books on a small rack and then distribute multiple copies of each book on other racks. So this is the way the students could easily pick up a book from any of the racks. So similarly, HDFS creates multiple copies of data in data blocks which are shared across different nodes that keeps them available if there is any failure of one of the nodes. And we have already discussed the architecture and its components. Let's see the details of each and every component. Then master node, that is the name node, is responsible for accepting jobs from the clients. Its task is to keep the metadata and then location, directory, and other details of the data blocks, and ensure that the data is required for the operation is loaded correctly and segregated into chunks of data blocks to share across the nodes. So that is main job of NameNode. And if the master node NameNode fails, then its secondary NameNode, which is a standby copy of NameNode, that will get activated and it will maintain the jobs going. So even though if we have two name nodes, one is a primary, another one is secondary, only one name node can be active in a cluster at a time. So that is the main point that master and slave architecture follows. And as we have already seen, the data nodes are within the slave. And HDFS exposes file system namespace that allows user data to be stored in files. and a file is distributed as a block into different nodes. And we already have seen the architecture. Let's move how files are stored. If you see in the picture, the data blocks in HDFS, like here, if we have 400 MB of file, it will be divided into 4 blocks, as we have default setting of 128 MB data block size. So first 3 blocks are of size 128 MB, and then the fourth one 16 MB. Overall it is 400 MB, which means the data block size can be default 128 maximum, and it can even store lesser size of data. If you set default size 256 MB, then this file could have been divided into 2 blocks, which is block A 256 MB and block B, which has the remaining size 244 MB. So either way, it will divide the data into chunks as per the size we have set in our configuration file. So that is how the data is stored. And we have the main advantage of HDFS, which is replication of data and fault tolerance. As you see in the picture, the input file is divided into 5 blocks here in the first diagram, A, B, C, D and E, and then the first node contains A, C and D blocks, and other ones, as you have seen, if you see for A, the replica is stored in node 3, which is highlighted in the same color, and then node 5. So if node 1 fails, then when we are accessing data, the block A will be accessed either from node 3 or node E. So we are designing to store data blocks of replicas of data block for any individual block, such that if there is any failure of a node, then it can be accessible from other available nodes. So likewise for the other blocks B, C, D and E, if you see, the same block is not stored on the same node. So that is how we can achieve fault tolerance for replication of data. In the second diagram, if you see, it is similar. Block A, block B, block C, which are of 3 chunks of file XYZ. So if you see, the block A of file XYZ has a main copy in D1, data node 1, and then data node 2, and then data node 4, which makes it available even one of them is not available or down. So the main point you have to remember here is each block is replicated into default 3 copies to different nodes. So in the interview question, or anywhere, you have to remember that how many replicas will be there in HDFS for a node block. You have to remember it is default 3, and it can be increased depending on our requirements. So this ensures the data availability even if some nodes are not available, which is fault tolerance of replicated data. Let's move to next section. So As we have seen in the architecture, the read and write, when there is a client request of read and write, then the resource manager will give the location and directory metadata of the data block so that client can access the data directly. So as we have main components, NameNode, secondary NameNode, and then DataNode, the file system and metadata are the other components of HDFS. So if you observe the read and write workflow diagram here, the HDFS client, which is a client, it can be a program or somebody trying to access the data using API. So the client request to create write and flows, it will be going to distributed file system and then FS data outstream. So client is basically a Java JVM client which resides in the client node. So these are from client side. So the client request from HDFS client via distributed file system goes to the master of our cluster, and then it looks into the resource manager data, that is metadata, file system and directory location details, and it picks the data block to be created and creates using a pipeline into the data nodes. So if you notice, the each data node is able to access each other's data. That means they can talk to each other and they can store the data blocks as we have replicas of each data block, and the details like metadata, file system and then location will be sent back to resource manager of NameNode, which is the master. That is how the entire create action will be completed. So once the data is completed, so it will master will send the complete notification as the process completion message to the distributed file system. So from there the client can read that the data is created and then successfully stored in the data node. Likewise, to write we have to do the same steps, but FS data output stream is required in middle, as you all know of the process of JVM. So clients write data by communicating with the name node to get block locations and then write to data nodes. So for reads, clients fetch the list of blocks from name node and read directly from the data nodes. This is all about read and write workflows. So let's see the important points about HDFS architecture, which is namespace, quotas, formations. So what is each concept is doing in our HDFS. So HDFS uses hierarchical file system namespace. So as you already aware, the namespace is nothing but the all classes or file system containing with under one name. So it supports file permissions, access control list, which is also called as ACLS. You will hear this term frequently. So you need to remember, and quotas on directories to control storage usage. That means there will be certain quota set for each client request or each operation to store the data in the data nodes. So HDFS space distribution among Hadoop applications, and from there Hadoop administrator does quota assignment. So and then it goes to HDFS storage, so which is distributed like above among different environment in the same Hadoop cluster. And then we have even something called space distribution by project size, which can be set using the incoming request. And there is the final one, HDFS space distribution by business, business team or user size. So there are four factors that decides the allocation quota. Then, as we have already seen, high availability and scaling is one of the features. So here is the graphical representation. So as we have seen, namespace. So we have NameNode 1, which has namespace 1, like NameNode K, namespace K, and NameNode N has namespace N. So each NameNode has one namespace which has been assigned to block pools, pool 1, pool K, pool N. So and from there it will go to common storage that consists of multiple data nodes, data node 1, data node 2 and so on, data node M. The HDFS supports standby name nodes and automatic failover. It scales horizontally by simply adding more data nodes. Horizontally, scaling is nothing but adding more storage in terms of data nodes so that there is a high requirement, then it is scaled successfully. So high availability is achieved and scaling is successfully done. So as we have seen, the block storage is scalable and namespace is assigned with different pools. So this is about high availability in the HDFS. And here is the representation for HA name node. HA is nothing but high availability. So here we have again two name nodes, among which one is active, another is in standby mode. You can read more details from here. We have already discussed read-write operations will be performed via master name node depending on which is active. So there is a failure case, then automatically secondary name node gets activated, then the request will be accessed via secondary name node, which is nothing but in active state it is a master name node. So let's see what are all the real world cases we are using HDFS. Number one is telecom. For telecom domain, we can store and process call data records, CDRs, for the analysis and then for any kind of reports generation. And in retail, it is also same. We can store huge amount of retail data because nowadays the customer incoming and outgoing request of checking for the products is used. If the retail business wants to store each and every click of the user, then the data generated will be more than petabytes. So analyzing customer behavior and transaction logs can be done using HDFS. And then banking. In banking, we have fraud detection through large scale transaction analysis can be achieved using a distributed system, which is HDFS. And healthcare, so analyzing medical records and patient data for insights. And social media, managing user content, logs and recommendation system is a part that can be achieved using HDFS. So that is all about concepts, understanding of HDFS. And then there are few other points that we will discuss like NameNode and its main tasks as part of transaction log and then edit log. So there are so many, and even we can discuss in the next video about HDFS command line commands, and then what are all the use cases that we will be doing a particular operation we will be discussing, and metadata and data node, what are all the activities that are happening and what are all the configuration files, like we have mapreduce.conf, and then we have other configuration files. So we will even discuss replication, fault tolerance, reliability in detail, and there are certain replication methodology like block replication architecture, and then method we have. So all those topics we will be discussing in further videos, and if you have any questions, please comment. I'm happy to help. Thank you for watching.